Okay, my friends. Now, in order to calculate a sample size, which is a very, very common question in differential stats, we have to go back to the idea of a margin of error. So we know that for a proportion, the margin of error, whatever it is, we've been calculating this in class, is equal to, and it's got these components to it, right? It's got a confidence multiplier, which is how wide we want that interval to be. We've been using 2 for that, for 2 standard errors for quite some time. And speaking of standard error, that's the other part of this, which is the square root of, and this is the part we kind of goofed around with in class, p hat times q hat over the sample size n. So when you look at this thing, it's got a number of pieces. It's got the actual margin of error that it's equal to, which is one piece. It's got the confidence multiplier, which is a second piece. And it's got p hat and q hat, which are, I guess, technically a third and a fourth piece, even though one of them is the same. One of them is found from the other one. And then you got your sample size. So in this little formula, there's actually 5 different variables, 5 things that can be varied. But if you know 4 of them, you can get the 5th one, which is how we calculate a margin of error. You know, we know these 4 things, so we can get that thing. Well, it works for any of the variables. If you know, say, for example, these 4 things, you can get that. So we can solve for the sample size if we establish all the other things. The big part of this video is going to be getting that n by itself on one side. Because right now the formula is solved for margin of error. You could solve this formula for any of the variables. But there's no reason to, except for the sample size, because this is a question that I'm often asked. How big a sample do I need? So let's do it. Okay. First thing I want to do, a little bit of algebra here. In case you're sick of this, you can just skip to the end. I'm going to divide by z first. What that'll do is it'll put it over here under the margin of error. So it's going to be margin of error divided by z equals that big square root thing here. Square root p hat q hat over n. Okay. This square root's kind of annoying. So let's square both sides to get the square root gone. That means we have to square this quantity over here. Margin of error over z squared equals, and now it's just p hat q hat over n. But now I'm out of space, so I'm going to snap my fingers and move that equation to the top. Okay. So n's in the denominator. I'm going to use an old school algebra skill that if you have a proportion, which is what we've got right here, you've got a fraction equal to a fraction. I can invert both the fractions and the fraction, and the proportion is still true. It still equals. So I'm going to put z over the margin of error squared equals n over p hat q hat. All right, this is looking great. And then all we got to do is move the p hat q hat to the other side. That's going to be p hat times q hat times all this. Equals n. And that, my dear friends, is how you find a margin of error. Now, I know what you're thinking, maybe thinking. If we're trying to figure out what the sample size is in order to do the study, how the heck can we know what the study's proportion is going to be, right? I mean, the reason you do a study is to establish what p hat and q hat are. So why assume that we know it already? And so we're not going to. We're not going to at all. Here's the deal. We know that p hat and q hat add together to make 1. They add together to make 1. So for example, I'm just going to give you a couple little values that p hat and q hat could be. It could be that p hat is like 10%, which means q hat is 90%. Or it could be that p hat is 2% and q hat is 80%. Or anything really. 30% 70, 40% and 60. It could be any of these things. multiplying them together, though, you're gonna see something kind of cool. If we multiply these things together, p hat, q hat, 0.1 times 0.9 is 0.09. 0.2 times 0.8 is 0.16. 0.3 times 0.7 is 0.21. 0.4 times 0.6 is 0.24. If we keep this list going, look what happens. Let's say it's 0.5 and 0.5. Well, that's 0.25. And then let's say it flip-flops. Let's say p hat gets bigger. 0.6, 0.4. This is now 0.24. So if 0.4 and 0.6 and 0.6 and 0.4 multiply to make the same 0.24. And that will continue all the way down. If it's 0.7 and 0.3, it's going to be 0.21. So what you're beginning to see is, even though p hat and q hat always add to make 1, which they always do by definition, they multiply to make different values. And here's the bit that kind of throws back to algebra 2. The largest possible product of these two things is going to be 0.25. Can't be any bigger than that. So since that's the largest they can be, or I should say it can be, the largest the product can be, and we're trying to make a sample size that gets us the best data, wouldn't it make sense to make this as large as it could be? I think so. So rather than assume some value of p hat, just set p hat and q hat equal to 0.5, and that makes the sample size as large as possible for confidence reasons. So we just change, actually I'm not going to erase it, I'm just going to change it to 5 z squared over the margin of error squared. Yeah, I'm going to put those parentheses back on that. Sorry, it looks weird with the word. You know, the 2 might get lost up there. And that's going to be your sample size. So what's cool about this is you only need 2 things. How confident you want to be, which is what that number of standard errors is, and whatever maximum margin of error you want. So if you specify how off you're willing to be, that goes in the bottom. The confidence goes in the top. And what's actually really kind of cool, if you operate at 95% confidence, which a lot of times we do, that is going to be 2. 2 squared is 4. This is 4. That's 1/4. So that numerator actually equals 1. So if you know you're always going to be at 95% confidence, that's even kind of cooler. Then it's just 1 over whatever the margin of error is squared. And make sure also that the margin of error is a decimal. We often say it as a percent, like 3%, but that really means 3 over 100, which is 0.03. And you'll see that in the next question you'll be working on. All right, that was fun. Get to it.